Hi everyone, welcome back. In today's video we're going to be having a look at conflict-based search, CBS, in a nutshell. So CBS is an extremely important algorithm that underpins a lot of state-of-the-art in the area. The algorithm itself is state-of-the-art in multi-agent pathfinding, MAPF, and it's actually used under the hood for a lot of different other state-of-the-art algorithms that actually run CBS to help it with, believe it or not, resolving conflicts. So conflict-based search is actually very easy to understand, but it's extremely performative, and it's essentially doing this large restructure of the way we actually view and represent the problem in the search space as states themselves. So first off, the base idea of CBS really is that we're reframing the problem. Instead of trying to search over individual agent moves along the way, well, what we're doing instead is we're reframing. We'll see soon that a state actually represents an entire solution, right, including all paths of all agents. Instead, what we're going to be actually searching over is going to be conflicts, right? So we've identified that it's conflicts that are often the challenge in MAPF problems, or at least one of the challenges. So we're going to tackle them directly, straight in the way we represent the problem and in the search space itself. So some strategies and properties of CBS. Essentially, what's really exciting, first actually, this is a complete and optimal algorithm, which is exceptionally exciting. We've seen that things like prioritized planning are not able to offer these guarantees. And CBS is still going to scale relatively well, better than centralized A*, but still have limitations. I'll draw that up at the end. So what's actually happening though is that CBS is essentially going to be doing a divide and conquer technique over conflicts. So what that means is essentially when we identify a conflict in a solution set, right? So essentially a state, a potential solution. Well, we'll identify a conflict and go, okay, so obviously it's not a valid solution just yet. And what we're going to do instead is replan under two different assumptions. So what we're going to be doing is actually splitting the node into two different worldviews. So we're kind of building up these almost like parallel worlds as we search over time. In one view, right, you say agent 1, you get right of way, you get to go. Agent 2, you can't be there. In the other worldview, you swap it, right? So agent 2 will have priority instead. What's actually going to happen, the way this algorithm works, is it's going to be a multi-level algorithm, which you'll see is kind of common in a lot of the state-of-the-art hereafter in MAPF. So how this works really is that at the high level, this is what we have standardly been considering search. So at the high level, you're doing the standard search tree that we expect. We're going to be searching, as we're saying, over conflicts, right? So what we're going to be doing is identifying, I forgot a Y, that's very silly. So you need to identify conflicts, and we're going to split on them by adding in constraints. So we're going to say, as I just said before, you can be here or you can be here. But more explicitly, the constraint says agent 1 is not allowed to be here. Agent 2 is not allowed to be here. The low level comes into play because in a single state, right, we needed to obtain solutions. We need to obtain paths for the actual individual agents. So at the low level, what you do is you run another solver, something like vanilla old A*, right? And A* is going to be returning to you an optimal solution for each agent individually. And so we're planning them with no regard for any other agent. But as we'll see, when I draw this up, well, over time, we're adding more and more constraints in. These essentially just in like a grid world, for example, these are just like obstacles. So, hey, this location is blocked at this time. And so your A* will plan around that, right, as more and more constraints are iteratively added. This is why it's kind of a divide and conquer technique, because essentially over time, you're dividing the space up more and more, and you build up these sub-problems until we can finally find a solution. Right, and we are guaranteed to find a solution, and it will be the optimal solution. So let's have a go at how this actually looks when we look at a real problem. So in the real problem over here, the standard way, right, we run the low-level solver first. I'll put up the pseudocode of the algorithm here, just to maybe help out. But yeah, so in the first sense, both agents just plan their individually optimal paths with no regard for each other. They have no knowledge that they are obviously having a conflict at this location here. So how does this begin? Well, we begin at the root node, And the root node, hopefully, could possibly have a conflict-free plan. So if all your agents are in different parts of the map, they happily just plan their paths. Well, ta-da, it would be done. Happy days. Obviously, that's very unlikely to happen in a lot of these congested problems, such as this. So in this world, what happens is that we have identified a conflict, and so we will branch. You'll note that essentially CBS is going to be producing a binary tree because we branch on two worldviews. You get to go, or you get to go. Now, the other aspect of this before I continue is that, well, it's similar to A star, right? We're going to be ranking the promise of each node, right? So similar to the F value. So each node also has to have a number. This is going to be whatever your objective function is. So is it sum of individual costs? Is it your make span? Whatever it is. We're just going to use sum of costs because that's a very common measure. So here it would be, what are the costs of the solutions thus far? Well, the green agent, agent 2, got 1, 2, 3, 4. And then the pink, 1, 2, 3, 4. So ta-da, the cost so far in the root node, we're saying optimistically, we think both agents can get there in 4. The whole solution's cost is 8. Ta-da. Does it work? You identify, you look for collisions. Unfortunately, we've found one. We're going to have to split, okay? So we need to add in constraints. So what does this look like? So this is what is called the logical not operator, okay? Also, I kind of forgot to say before, but in terms of, we're dealing with this idea of constraints, which is actually kind of borrowed from the whole field of constraint programming, constraint satisfaction and things. So this is a field of study and optimization that's probably even as large, or at least larger than MAPF. And it's cool how we're able to borrow some of those concepts and bring them across into the world of MAPF. So this is saying, it's essentially saying not. So when I write out this constraint, we're saying this is not allowed to be true, okay? So what we're saying is agent 1, we have to specify which agent. Agent 1 is not allowed to be at location D2. And the last thing we need is, because it's a time-based problem, you need to say when it's not allowed to be there. So this would be at time step 1, 2, 3 in this situation. We'll do the exact same on the other side. So here instead is the opposite worldview. See how we're kind of like splitting, almost like parallel universes? In one, agent 2 gets priority. In the other one, agent 1 gets priority. So in the constraint then is saying, hey, agent 2, you are not allowed to be at the same location D2 at time step 3, okay? So that is really interesting here. Now what we do again is we calculate the sum of the costs of these plans. So in the worldview where agent 1 is not allowed to be here, well, it doesn't really have a good, like a detour takes a lot of time. So its next optimal plan is to wait one time step somewhere, which increases its cost from 4 to 5. So what that means is one agent gets there with 4, that's 2, and the other one gets there with 5. So we see that the plan cost is actually increased by 1, okay? If we do the other worldview, well, in the optimistic sense, it said that essentially the green agent is not allowed to be here at this location. Well, waiting is actually going to increase the cost, but it has a better option available to it. Why doesn't it replan, right? So this still has a cost of 4. What that means in the optimistic sense is we're still looking good, okay? So we think, hey, maybe this will work. It has 8. We check. Oh, no. Of course, unfortunately, we see that there is another conflict and we need to deal with this. So we would split. Now, based on these two nodes, if this one was a lower cost, we would have expanded this one first and checked for collisions. But because this has a cost of 8, we expand to this node next, and that's where we identify the collision, and that's then where we split again. Okay, so now we have 2 more constraints. It's going to be the similar thing, right? So agent 1, but now it's actually at location C2, and now it's earlier in time, it's at time step 2, and then the other side of the path is going to be agent 2, same location C2, and at time step 2 as well. Okay, cool. So then let's again think about the cost of these solutions. Well, if you actually notice, again, in this worldview, pink has to wait one more time. So you can convince yourself again it's a cost of 9. Now in this worldview, again, green, instead of waiting, actually still has one last trick up its sleeve. It tries to go this way instead, still thinks it's like in an optimistic sense, yeah, your optimal path is 4, you can get there. So what that means is that this has a cost of 8. This time we say, okay, cool, we'll expand this node Alas, right, alas, we have identified that there is one more conflict, and we will have to resolve this by splitting. Now, we have 2 new children. Similar to before, this one is the version where pink waits. Now, green, this time, tries to look for another reroute, figures out that it finally doesn't have anything of cost 4. At some point in time, it's going to have to wait. That means that this pushes to 9 now. Okay, so to write up the constraint as well, sorry, so not 1, it's not at location B2, and not at time step 1. Similarly here, it is not 2 at location B2 at time step 1. Okay, so now we have 4 nodes in the search tree at this high level, right, that have a cost of 9. Which one do we expand? Any of them, right? It's up to tie breaking, doesn't matter. So this was expansion 1, right? Then we expanded this one. Then we expanded this one. Next, it really doesn't matter. Maybe we just choose this. And ta-da, we've finally concluded that we find a node. We look for conflicts. We see in this version of the world where one of the agents waited, there were no conflicts. Ta-da, collision-free path. And we're actually guaranteed that this solution has the optimal cost, right? The optimal cost in this world was only a sum of individual costs of 9. So that's exciting. So this is CBS. I think CBS is actually very intuitive to understand. It does require this little reframing of ideas in terms of high and low level, this idea of branching and replanning, and technically the idea that, right, that states represent an entire solution set, the full paths of all agents. So that is interesting. But CBS is very performative. And also let's talk then about its kind of scaling. So how good is CBS? Well, centralized A*, as we saw before, this can only really solve, it only gets up to 10 agents and it starts to break down. That's obviously a massive issue, and we've talked about how centralized A* does not scale. Well, CBS does perform substantially better. So CBS scales to, we say, I think it's variant, but we say often like a few dozen agents. So sometimes the number's thrown out like, with some enhancements, well not enhancements, with some good implementation, you can get to 30 to 50 agents before things really start to break down. This is not to say CBS is perfect, because CBS is still trying to do optimal search in MAPF. Well, optimal search is extremely difficult. MAPF is an NP hard problem, and oftentimes in difficult or large problems, we really just can't spend the time to actually try to find an optimal solution. It just won't work. We won't even be able to find a solution at all. So there are a few things there then. So first, you'll see that the actual leading state-of-the-art methods, things like large neighborhood search and lazy constraint addition search, LACAM. So LNS, for example, uses CBS under the hood as part of its Lego blocks to try to resolve individual groups of agents. So CBS is still really important for informing these, but the reason things like large neighborhood search will perform better is because it's embracing something called anytime search behavior. So the leading method to solving a MAPF, just because of its difficulty, is actually instead to try to find a good enough solution quickly, and then iteratively improve within whatever time budget you still have available to you, right? Continue to improve the solution. Hopefully then, if given enough time, LNS will find an optimal solution. So that is why CBS is kind of limited. The really cool thing, I won't be talking about it in this video, but there's essentially a bunch of other algorithms. So eCBS is enhanced conflict-based search. Well, with some enhancements, these can now scale much further to hundreds of agents, which is quite exciting. eCBS is essentially using focal search at both the high level and the low level. And when you combine those together, we get eCBS, and it can push CBS much further than it would otherwise be able to do. And there's a bunch of other, CBS is really built upon, there's a whole family of techniques that really mean, right, like it's a good way to view the problem and to tackle the problem. Obviously conflicts are integral in the actual difficulty and challenge of problems in this area, and things like symmetry constraints and whatnot can be applied to CBS to increase behavior further. Otherwise, thanks for watching, and this has been conflict-based search in a nutshell. Thanks.